Alright, so today's lesson we're going to focus on series circuits only, and we're going to go over Kirchhoff's current and voltage rule for series circuit, and then I'm going to talk about equivalent resistance. So let's draw a basic series circuit with some resistors. How about I just put in two resistors? So 1 and 2. There we go. Two resistors. Terribly drawn, but two resistors. Okay. Now, if we were to have, say, a bunch of electrons moving through here, every single electron would go through the first resistor, every single electron would go through the second resistor, and they would all come back. It's a series circuit, so there's only one path for them to take. Since we have all the electrons moving through the same path, what we can say is the current, let's call this resistor 1, so the current that goes through resistor 1 must be the same as the current that goes through resistor 2, which must be the same as the current that goes through the battery, which we usually call the total. So this is Kirchhoff's current rule. In a series circuit, the current through every resistor and the battery is the same. Okay, well let's follow one single electron then. If we follow one single electron, let's make this green. We follow one single electron. It gets a certain amount of energy at the battery. Let's say 9 volts, for example. So if it gets 9 volts at the battery, it comes and it has to go through the first resistor. And so it has to give up some of its energy. Let's say it gives up 4 volts, for example. It'll depend on the two resistors, but we'll get to that later. Let's say it gives up 4 volts. And then it continues over to the next resistor. It's only got 5 volts remaining because it gave up 4 volts at the first resistor. So it's going to give up the remaining 5 volts. It'll always use up all of its energy before getting back to the battery. And so what does this mean? It means if it gains a certain amount of total voltage at the battery, and it loses some voltage V1 at resistor 2 and some voltage V2 at resistor 1 and resistor 2, then the sum of those voltage losses must be equal to that voltage gain at the battery. That is Kirchhoff's voltage rule for a series circuit. The last thing I want to talk about is equivalent resistance. What does equivalent resistance mean? It means if I were to take this circuit, which for example has two resistors, and I were to create a new circuit with only one resistor, what would the resistance of that resistor need to be so that it is an equivalent total resistance to the previous circuit? So I want the same current going through both circuits because the resistance is the same in both circuits. It's just I've replaced it with one equivalent resistor. Now, if we look at the current going through a series circuit, you realize, well, the first resistor slows it down and the second resistor slows it down even more. So it makes sense that the total resistance would simply be the sum of those resistors in series. So this I would call R, sometimes R total, or if you like, R equivalent. And in a series circuit, you add those resistances to get total resistance. Now I put in this nice visual here for a series circuit. So you can imagine, say, the battery giving a certain amount of electrical potential energy. Now in this sort of analogy, we have water lifting up. So this pump here, this water pump, is giving the water a certain amount of gravitational potential energy. In either case, we have some sort of potential energy being given. And then as it falls down, we have these water wheels that slow it down. So these water wheels, it's giving up energy as it comes down, converting it into whatever loads you have attached. But each load, in this case the water wheel would spin, so it gets converted to kinetic energy, but it also slows down the water, causing some sort of resistance. And so the current gets reduced. And if we have another water wheel, that same water goes through this water wheel, again, converting its energy into kinetic in this case because it spins, and slowing it down. One pathway. Right? I think it's a good analogy. But you can also think of what I said in yesterday's lesson of the highway example for a series circuit. So now that we've done that, let's try an example. We're going to solve just a series circuit. Tomorrow we'll do parallel circuits, and then we're going to mix them together. So we start off with the basics. So in this example, it asks to determine the current, total resistance, and voltage drops through all the resistors in this circuit. So what do we have here? We have the voltage supplied by the battery. That is 200 volts. We have 3 resistors hooked up in series. The first one being 20 ohms, the next one 50 ohms, and the next one 30 ohms. And I need to figure out the total resistance, the total current, and the current and voltage in each resistor. So we need to solve for every possible thing we would want to know in this circuit. Alright, so first thing, we can figure out total resistance. Because total resistance is just the sum of all the resistors in series. So R1 plus R2 plus R3. Where in this case we have 20 ohms plus 50 ohms plus 30 ohms. So our total resistance then in this circuit is 100 ohms. Okay, so I can write that over here if it helps. We sort of like fill out the diagram. 100 ohms. Now, whenever you're looking at a circuit, if at any point, say at a resistor or at a battery, you know 2 of the 3 pieces of information, those 3 pieces of information being resistance, voltage, potential difference, or current, if you know any 2, then you can use Ohm's law to solve for the missing third. So across the battery, we know total resistance and total voltage. So if you remember Ohm's law, this is probably what you remember. Potential difference equals current times resistance. Okay, but we can solve for current in this case because we know resistance and voltage. So rearranging, the total current equals the total voltage divided by the total resistance, which in this case is 200 volts divided by 100 ohms, which gives us 2 amps. Alright, so we know total current is 2 amps. And solving circuits really is like solving a puzzle. I sometimes like to think of it as like solving a Sudoku puzzle, where once you get one number, that helps you get the next number. And once you get that number, that helps you get to the next number. Right? So it's like a series of puzzles that you can just constantly solve for the next one. So once we got total resistance, that helped us find total current. Now that we know total current, and we know Kirchhoff's current law, which says that in a series circuit, the current through all resistors and the battery is the same, I know that I1 is going to be 2 amps, I2 is going to be 2 amps, and I3 is also going to be 2 amps. Now all we need to do is solve for the voltage drop across each resistor. But that current that we found out using Kirchhoff's law has given us the next piece of the puzzle. And since we know 2 pieces of information for every resistor, I can go ahead and use Ohm's law here, V equals IR, to solve for the missing voltage. So in this case, 2 times 20 is 40, so we get V1 equals 40 volts. Over here, we have 2 times 50, which is 100, so V2 equals 100 volts. And over here, 2 times 30 equals 60, so V3 equals 60 volts. And just like Sudoku, there's a way to check to see if you've made a mistake. In Sudoku, if you have, we have two of the same number in that row or column or box. In this case, we can now use Kirchhoff's voltage law to check to make sure that works. Kirchhoff's voltage law says, well, the total voltage gained at the battery is equal to the sum of the voltages dropped or lost at each resistor or load. So 200 should equal 40 plus 100 plus 60. In this case, it does, right? 40 plus 100 plus 60 is 200. So that's a check we can do on our own work to let us know that, yes, it's working. We did it right. Okay? And now we've solved the puzzle. We're done.